Which data points are close to each other? Which ones are fundamentally similar? And which direction should we move to improve our predictions? Humans look at a dataset and see rows and columns like a standard table. But algorithms, they see something entirely different. They see pure geometry. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
It's really fantastic to dive into this material today.
Yeah, we have a massive topic to unpack.
We really do. And I want to speak directly to you, the listener, for just a second before we start. Chances are you're coming into this deep dive as a Python developer.
Right.
You're highly proficient at writing logic, building functional applications, creating loops, setting up API endpoints.
You're comfortable in the world of explicit instructions.
Exactly. But stepping into the architecture of machine learning and artificial intelligence, it requires a totally different framework.
It really does. It often feels like you're trying to learn an alien language.
It does. And our mission today is to completely rewire your mental model of what data actually is. Right now, when you fire up a script and load a data set into a pandas data frame, you see what any human is conditioned to see. A spreadsheet. You see an index on the left, headers across the top, and neat little rows of values.
It's a highly literal two-dimensional grid.
Right, but algorithms, they do not understand grids. They operate purely in the realm of vast, high-dimensional geometry.
Which is wild to think about.
It is. So today, we are going to dismantle that spreadsheet and rebuild it as a geometric universe, allowing you to see your data exactly the way an AI model sees it.
Let's ground that immediately, because moving from a pandas data frame to a geometric universe is it's a pretty heavy conceptual leap.
It's a massive leap.
Yeah. If I open a CSV file, I'm looking at discrete records, the indexing feels very arbitrary. Like row 0 might be a customer from New York and row 1 might be a customer from Tokyo. Their placement next to each other in the table doesn't mean they have any relationship. It just means they were entered into the database sequentially.
Exactly.
So you're suggesting that this literal tabular view is actually limiting our ability to design good machine learning models.
It is severely limiting. A table is just a human-computer interface. It's a translation layer designed entirely for readability.
For human eyes.
Right. An algorithm entirely strips away your headers, your row numbers, your alphabetical sorting. It translates those raw numbers into spatial coordinates.
Right.
The goal for anyone wanting to be truly industry-ready in data science or AI engineering is to develop an intuitive spatial understanding of fundamental math concepts. You need to stop thinking about sorting rows and start thinking about navigating space.
We should apply this to a real-world industry context so we can trace the exact mechanics of that translation.
Let's do it.
Let's take a classic predictive modeling scenario. A bank trying to predict loan defaults based on customer profiles. In our database, we pull up a typical customer. Let's say their profile shows an annual income of $40,000, a credit score of 620, and an age of 25.
Okay, classic data set.
Right. In the traditional developer mindset, I just query my SQL database and I get a record back. It's just text and integers on a screen.
So to perform the mental shift, I want you, the developer listening to this right now, to visualize an empty, three-dimensional physical space.
Like a room.
Exactly. Picture the room you're currently sitting in. You have a floor, you have walls, and you have a ceiling.
Got it.
We are going to map the variables from your SQL query directly onto the architecture of this room.
Okay, so how do we label the room?
Let the width of the room, running along the floor from left to right, be the income axis.
Left to right is income.
Right. Let the depth of the room, running along the floor from front to back, be the credit score axis.
Depth is credit score.
And finally, let the vertical height of the room, from the floor to the ceiling, represent the age axis.
Okay, so standing in the corner of this room, I'm looking at 3 intersecting lines. The floor stretches out, representing wealth and credit, and the vertical space going up to the ceiling represents time.
Perfect. Now take the data for that specific customer, 40,000 for income, 620 for credit score, and 25 for age.
The single row from our database.
Yes. In this framework, that customer is no longer a sequential row in a table. That customer translates to a highly specific, immutable coordinate floating in the air inside that room.
So I would physically walk out along the floor to the 40K mark on the income line,
Right.
and from that spot, I walk forward to the 620 mark on the credit score line.
Exactly. And then you would take a ladder and climb straight up until you hit the 25 mark on the age line.
And if I leave a glowing dot right there in the air, that dot is the absolute representation of my customer.
That dot is your customer. That means the term feature space, which shows up in almost every foundational ML tutorial.
Oh,
Yeah, feature space is literally just the geometric environment formed by the variables we choose to include.
that captures the definition perfectly. Every single row in your entire dataset, whether it's 10 rows or 10 million rows, becomes a separate autonomous point floating in this space.
Yes, if you queried 10,000 customers, your algorithm doesn't see a long scrolling list.
It sees a dense cloud of 10,000 dots hovering within this room.
And crucially, every new feature you add, every single column you append to your data frame, spawns a new physical dimension.
And that concept of adding columns introduces a massive cognitive wall for humans.
It really does.
I mean, I can easily picture the 3D room. Income, credit score, age, that maps perfectly to the physical world we live in. But in a modern industry ML pipeline, no one is training a model on just 3 variables.
Never.
We are looking at income, credit score, age, transaction frequency, average transaction value, zip code demographics, device type, session duration, and on and on.
It scales incredibly fast.
We routinely build feature spaces with hundreds, thousands, or even millions of dimensions. Human visualization completely breaks down past 3D.
It does break down for us visually, but mathematically, the architecture remains completely identical.
That's the crazy part.
The algebraic rules governing how a point behaves in a three-dimensional room scale flawlessly to a million-dimensional room. You cannot picture a room with a million intersecting walls, but an algorithm navigates that hyperdimensional space effortlessly.
So to the machine, adding 1,000 columns just means calculating coordinates with 1,000 numbers instead of 3.
Exactly. The fundamental geometry doesn't change.
Okay, so we have established this feature space, and we have this cloud of dots representing our customers. But a floating dot is just a static location. It's a coordinate marking a spot. When we look at the actual mathematical representation used in machine learning libraries, we don't just use dots.
No, we don't.
We use vectors.
Vectors serve as the absolute foundational language of machine learning.
How does a vector change the visual of the dot?
Instead of visualizing that customer as a detached dot hovering aimlessly in the room, you need to visualize an arrow.
An arrow.
An arrow. You draw this arrow starting from the very center of the space, the absolute corner of the room where the floor and walls intersect at 0, and you extend it outward until the tip of the arrow perfectly touches that customer's glowing coordinate.
Let's analyze that starting position, because anchoring the arrow at 0, 0, 0 seems like a very deliberate choice. What does the corner of the room actually represent in the context of our data?
Anchoring it at the origin point carries significant structural meaning. That 0 coordinate represents the 0 customer.
The 0 customer.
Yeah, it is a theoretical baseline entity possessing absolutely 0 income, a credit score of absolute 0, and an age of 0.
It represents a total absence of features, a blank slate.
Right, so if the tail of the arrow sits at nothing, and the tip of the arrow sits at our customer making $40,000, then the arrow itself is a measurement of variance from that baseline.
That is the crucial takeaway right there. Every vector arrow is a literal physical measurement of how much a specific data point differs from nothing.
Yes. A vector possesses 2 intrinsic properties, direction and magnitude.
The direction shows the specific combination of traits, right? Like pointing on a trajectory that favors a younger age with moderate credit and lower income.
Exactly. And the magnitude is the physical length of the arrow. It indicates the sheer volume or intensity of those traits.
In the context of a Python array or a PyTorch tensor, a vector is simply an ordered list of numbers.
But geometrically, it is always this arrow pointing outward from the void.
Let's connect this to the terminology a developer encounters daily when reading documentation. We constantly see phrases like feature vectors, word embeddings, image embeddings, or model weights.
All the time.
This geometric framework implies that all of these terms are fundamentally describing the exact same thing.
They're all entirely interchangeable concepts geometrically.
Real.
Yes. When you feed a text string into an embedding model like Word2Vec or an LLM, the algorithm reads a word like king, processes its semantic relationships, and outputs an arrow pointing to a specific coordinate in a high-dimensional room.
Wow.
When you pass a photograph of a cat through a convolutional neural network, the image is mathematically dismantled, analyzed for pixel patterns, and ultimately transformed into an arrow.
Even the internal parameters.
Even the internal parameters, the weights of the model that govern its logic, they are just vectors. Everything, without exception, must be translated into an arrow before the machine can process it.
If everything is an arrow in a room, the obvious next question is how the machine extracts value from that arrangement. Why do we go through the computationally expensive process of converting millions of database rows into millions of arrows?
We do it because geometric space allows us to mathematically define relationships.
Relationships between the records.
Yes. And that leads directly to the core mechanism of predictive modeling calculating distance to measure similarity.
Let's bring a second customer into our bank loan scenario to see how this distance calculation actually works.
Okay.
Customer A is at $40,000 income, 620 credit score, and 25 years old. Now let's plot customer B. They have an income of $42K, a credit score of 630, and they are 26 years old.
Very similar numbers.
Right. If we plot that second arrow in our 3D room, the tip of customer B's arrow is going to end up physically hovering right next to the tip of customer A's arrow.
They will be in extremely close proximity. And this visual clustering translates to the single most important axiom you need to lock into your mental model.
Which is?
In the geometry of machine learning, physical closeness equates to fundamental similarity.
Closeness is similarity.
Yes.
So the algorithm assumes that because their coordinates are clustered together in the feature space, their real-world behaviors will also cluster together.
The assumption is that overlapping features generate overlapping outcomes. If historical data shows that customer A ultimately defaulted on their loan, and the algorithm sees that customer B's vector is geometrically sitting right next to customer A, the system will automatically flag customer B as a high risk for default.
Because they were physically close in the room?
The entire predictive infrastructure relies on the premise that nearby points share similar target variables.
The intuition makes perfect sense, but the developer in me wants to know how the algorithm actually executes that measurement. We can't just look at a scatter plot and eyeball it.
No, the computer needs hard math.
If I'm writing the code, how does the computer mathematically deploy a tape measure between the tips of those two arrows?
The industry standard for this operation is called Euclidean distance.
Euclidean distance.
Yeah. The math behind it is something you likely encountered in high school geometry, the Pythagorean theorem.
A squared plus B squared equals C squared.
Exactly. You calculate the straight line hypotenuse by squaring the differences between the points, adding them up, and taking the square root.
So it scales up.
Euclidean distance is simply that exact same formula scaled up to accommodate any number of dimensions. You take the difference between customer A's income and customer B's income and square it.
Then do the same for credit score.
Do the same for credit score, do the same for age, sum them all together, root them, and you have a single scalar number representing the literal physical gap between those points.
And a small number means they are highly similar.
A small number means they are practically twins. A massive number means they share almost no common traits.
It is remarkably elegant that such complex predictive systems are essentially just iterating through a virtual ruler.
It really is.
This specific Euclidean measurement is the underlying engine for several major algorithms that a junior dev will encounter almost immediately.
It is the absolute backbone of distance-based modeling.
Yeah.
Take the k-nearest neighbors algorithm, or KNN.
Right, KNN.
It operates entirely on this principle. When a brand new, unclassified customer applies for a loan, the algorithm immediately plots their feature vector in the space.
It drops a new dot in the room.
Then it takes out that Euclidean virtual ruler and measures the distance from the new customer to every single historical customer in the database.
Wow. Every single one.
It isolates the k number of points, let's say the 5 points, that have the shortest absolute distance.
The nearest neighbors.
Exactly. If 4 out of those 5 nearest neighbors are known defaulters, the system denies the new loan application.
That exposes the mechanics beautifully. And we see this exact same geometry in unsupervised learning as well, like k-means clustering.
With k-means clustering, the algorithm isn't looking for predefined labels like defaulter.
It's just grouping data.
Right. It drops random center points into the space and continuously measures the Euclidean distance to group the nearest data points together into distinct geographic hubs.
And we even see it in traditional recommendation engines, don't we?
Oh, absolutely. If you listen to a specific song on a streaming service, the platform locates that song's vector in their audio feature space.
And then it finds the 10 tracks with the shortest Euclidean distance to that vector.
And queues them up in your playlist. Closeness equals similarity.
This all sounds incredibly robust until you start thinking about how real-world data is actually formatted.
Uh-oh.
Yeah. I can see a massive structural flaw here that routinely sabotages models built by beginners. We are plotting these points based purely on the raw integer or float values sitting in our pandas data frame.
We are, and that introduces a critical vulnerability into our spatial logic.
Let's analyze the axes we set up for our room earlier. Our income axis ranges from, let's assume, 0 to perhaps $150,000.
Huge numbers.
The numbers are massive. But our age axis only ranges from maybe 18 to 80.
Tiny numbers.
If our algorithm is blindly using the Pythagorean theorem to calculate distance, a numerical difference of $1 in income is mathematically identical to a difference of 1 year in age.
This is a phenomenal observation, and it highlights a phenomenon known in the industry as the units problem.
The units problem.
It is one of the most common reasons why a developer's first machine learning model will fail silently.
Silently, meaning no error codes.
Exactly. The code will compile perfectly, the model will output predictions, but those predictions will be structurally compromised.
Let's walk through the math of that failure. If customer X makes $40,000 and customer Y makes 40,001 the squared difference on the income axis is just 1.
Just one.
If customer X is 25 years old and customer Y is 26, the squared difference on the age axis is also 1.
To the raw algorithm, those gaps are identical.
But in reality, a $1 bump in annual salary is completely meaningless to a loan officer, whereas a full year of aging represents a tangible shift in life experience. We're feeding the algorithm false equivalence.
The algorithm is entirely agnostic to units. It does not know what $1 a year or a credit point is. It only parses magnitude.
So how does that affect our 3D room?
To understand how catastrophic this is, we need to look at what happens to the shape of the room. Because the income values span across tens of thousands of units, the physical length of the income axis becomes unimaginably long.
It stretches way out.
Conversely, because the variance in age is so small, capping out around 80, the age axis is incredibly short.
So the visual of our perfectly square 3D room is completely shattered. What does the geometry actually look like under these conditions?
The geometric space is warped and distorted into the shape of a long microscopic needle.
A needle.
A needle. The data cloud is stretched massively outward along the income dimension, pulling the points far away from each other horizontally. Simultaneously, because the variance in age is so small, the data is violently compressed along the vertical axis.
If the space is shaped like a needle, how does that corrupt the Euclidean distance calculation we just established?
It creates a massive bias. When the algorithm takes out its virtual ruler inside this needle-shaped space, any slight irrelevant variation in a customer's income will generate a massive physical distance.
Because the axis is stretched.
Right. Meanwhile, a massive critical variation in a customer's age will barely register as a millimeter of movement.
Wow.
The algorithm analyzes this warped geometry and logically concludes that income is the only feature that matters and age is completely irrelevant.
Because it's dominated by the sheer size of the numbers.
It will base all of its similarity calculations and therefore all of its predictions almost entirely on the variable with the largest raw numbers.
It effectively acts as an unintentional feature weighting system. The income column is shouting through a megaphone simply because it uses thousands, while the age column is whispering because it uses tens.
It's a great way to put it.
If our database happened to record income in thousands of dollars instead, meaning the value in the cell was 40 instead of 40,000, the entire shape of the room would shift and the model's predictions would completely change.
That is a terrifying reality for a developer who is just plugging raw CSV files into a .fit method.
The arbitrary choice of units dictates the outcome of the model.
This is the precise reason why the data science industry mandates the use of normalization, standardization, and feature scaling before any distance-based algorithm is applied.
Okay, so when a Python developer imports standard scalar or min-max scalar from Squirm preprocessing, what are those functions actually doing to the geometry of our room?
They are executing mathematical triage to fix the warp space.
Triage?
Yeah. A technique like min-max scaling mathematically constrains every single feature to fall strictly between the values of 0 and 1.
So it shrinks the massive income axis down and stretches the tiny age axis out.
Exactly. Standardization takes a different approach. It shifts the origin point to the exact center of your data cloud by subtracting the mean, and then it divides the values by the standard deviation.
Which does what?
This forces every axis to have a variance of 1.
So by applying those scaling functions, we are taking that distorted, stretched out needle and we are applying pressure to all sides until it morphs back into a perfectly balanced spherical geometry.
You are restoring an equitable spatial environment. Scaling ensures that every single dimension, regardless of whether it was originally measured in millions of dollars or fractions of a percentage, exerts the exact same geometric influence when the ruler comes out.
Without standardization, distance calculations are basically fraudulent.
They are. And since distance determines similarity, fraudulent distance yields terrible AI.
Okay, so we've established how crucial it is to measure the physical gap between the tips of these vectors and how to scale the room. But relying entirely on absolute distance introduces another massive blind spot.
Where are we going with this?
There are many real-world scenarios where the physical distance between 2 points is large, but the data points actually represent the exact same fundamental behavior.
Ah, yes. You are hitting on the core trade-off of spatial measurement. Euclidean distance measures the absolute magnitude of difference.
The raw gap.
But often, in predictive analytics, we don't care about the magnitude. We care exclusively about the underlying pattern or the direction the data is trending.
Which means we need new math.
This requires us to shift our mathematical toolkit from measuring distance to measuring angles. And that introduces the concepts of the dot product and cosine similarity.
Let's look at an intuitive analogy to separate distance from direction. We'll call it the Starbucks analogy.
I like it.
Imagine we are building a collaborative filtering recommendation engine for a coffee shop chain. We are tracking customer purchases.
Okay?
Customer A is a daily regular. Over the month, they purchase 30 lattes. In our future space, on the latte axis, customer A's vector shoots aggressively outward to the coordinate 30.
A long arrow.
It's a very long arrow. Now we have customer B. Customer B is a casual weekend-only visitor. Over the month, they purchase exactly 3 lattes. Their vector only extends to the coordinate 3.
Let's apply our Euclidean ruler to that scenario. We measure the gap between the endpoint at 30 and the endpoint at 3.
The absolute distance is 27 units.
In the context of a purchase history matrix, that is a vast geometric chasm.
If the recommendation algorithm is relying purely on Euclidean distance, it is going to classify customer A and customer B as completely dissimilar entities. It will refuse to cluster them together.
Because they are so far apart.
But from a business logic perspective, isn't that a massive mistake? Look at the actual preference. Both customers exclusively purchase lattes. They ignore the mochas. They bypass the black coffee. They never buy tea.
Their consumer taste is 100% identical.
The only variance is their available budget or their frequency of visits.
That is the exact flaw of relying solely on magnitude. Euclidean distance conflates volume with preference.
Which is bad for marketing.
Terribly bad. If the coffee shop introduces a new brand of oat milk specifically designed for lattes, you absolutely want to market that product to both customer A and customer B. But a distance-based model will isolate customer B because their vector is too short.
So how do we instruct our algorithm to ignore the physical distance between the tips of the arrows and instead recognize that the underlying pattern of behavior is identical?
We abandon the ruler and we bring out a protractor.
Then protract.
Instead of measuring the gap between the endpoints, we measure the angle formed between the 2 vector arrows originating from 0.
The angle between them.
This is the mechanism of cosine similarity, which is calculated using the mathematical operation known as the dot product.
Let's visualize that angle in our Starbucks example. Customer A's arrow extends out to 30 on the latte axis. Customer B's arrow extends out to 3 on the exact same axis.
Right.
Because they share the exact same proportional preference, only lattes, their arrows are stacked directly on top of each other.
They're pointing along the exact same trajectory. Because the arrows overlap perfectly, the angle between them is 0 degrees.
And what does that mean in trigonometry?
In trigonometry, the cosine of a 0-degree angle is exactly 1. Therefore, their cosine similarity score is a perfect 1.0, representing 100% directional alignment.
The algorithm sees that score of 1.0 and says, I'm going to ignore the fact that customer A spends 10 times more money. I can see that their behavioral vectors are pointing toward the exact same concept.
Cosine similarity brilliantly isolates directional preference by completely discarding the magnitude of the vectors.
It just looks at the trajectory.
Mathematically, it normalizes the lengths of the arrows, pushing them both out to a uniform length of 1, and only analyzes the gap in their angle.
The practical applications for this are staggering. It fundamentally drives how information retrieval works.
It drives almost all modern information retrieval. Think about a standard search engine query.
Okay, like typing something into Google.
You type a three-word phrase into the search bar. The system converts your query into a very short vector. You're looking for a comprehensive Wikipedia article on the topic, which, when converted to a vector, is massively long.
So a short vector and a long vector.
If the search engine used Euclidean distance, the short query vector and the massive document vector would be separated by an enormous physical distance. They would never match.
But by calculating cosine similarity,
The engine ignores the difference in word count and simply checks if the semantic angle of the query aligns with the semantic angle of the document.
that reframes how we look at large language models entirely.
It really does.
When we interact with ChatGPT or Claude, and the model is trying to determine which word should logically come next in a sentence, it isn't measuring distance. We are fundamentally just watching it calculate these geometric angles across billions of parameters to find contextual alignment.
That is the geometric reality of the self-attention mechanism inside a transformer model.
It's just angles.
When an LLM calculates the attention scores between words in a prompt, it is performing billions of dot product operations to measure the cosine similarity between those word vectors. It is constantly calculating the angles in high-dimensional space to determine which concepts are structurally related to each other.
This is such a powerful mental model. We now have distance to measure absolute gaps and angles to measure behavioral patterns.
Two critical tools.
But a major hurdle remains for our Python developer. When they import a dataset, they might have 500 columns.
Right, a massive data frame.
Intuitively, they know that not all 500 columns are actually useful. Some of those features are just random noise that will confuse the model. How do we geometrically determine which axes in our room actually hold valuable predictive power?
This introduces a pivotal operation in linear algebra projection.
Projection.
If vectors are arrows, projection is the mathematical equivalent of analyzing the shadows those arrows cast within the room.
I want to break down the shadow analogy carefully because projection is a concept that often gets buried under dense matrix notation in textbooks. Let's keep our single customer vector, our arrow, hovering in the 3D room.
To understand projection, imagine taking a powerful, highly directional flashlight.
A flashlight.
Stand directly above the arrow and shine the flashlight straight down toward the floor. In our model, let's say the floor represents the income axis.
The solid arrow is going to block the light, casting a distinct shadow down onto the income floor.
That shadow is the vector's projection onto the income axis. Now we must analyze the length of that shadow.
What does the length tell us?
If the customer's arrow is pointing predominantly downward, heavily aligned with the horizontal plane of the floor, the shadow it casts is going to be very long.
Because it's parallel to the floor.
Exactly. Conversely, if the arrow is pointing almost straight up toward the ceiling, let's say the ceiling represents the age axis, then when you shine the light straight down, the arrow will cast a tiny microscopic shadow on the floor.
We are measuring how much of the vector's total length is captured by one specific dimension. What does the length of that shadow actually communicate to the developer trying to optimize their feature set?
The length of the shadow quantifies the explanatory power of that specific feature.
Explanatory power.
A long shadow mathematically proves that the feature, the axis you're projecting onto, strongly influences the overall position of that data point. The variance in that feature captures a significant portion of the vector's trajectory.
And a tiny shadow.
A tiny shadow reveals that the feature contributes almost nothing to the vector's direction. It is geometrically irrelevant.
Let's translate that back to our data frame. If I have a column labeled favorite color in my lone default data set.
A completely useless column.
Right. And I mathematically project all 10,000 of my customer vectors onto the favorite color axis, and the resulting shadows are practically non-existent.
Then you have mathematical proof that favorite color exerts zero structural pull on the data.
I can confidently drop that column from my pandas data frame without losing any predictive accuracy.
You are identifying the exact mechanism for feature importance and dimensionality reduction.
That's what projection is used for.
Yes. Projection allows an algorithm to measure how much a vector aligns with a given direction. When you run a linear regression or when you attempt to compress a massive data set down to a smaller, more efficient footprint, the algorithm is fundamentally searching for the specific axes in the room that capture the longest shadows.
Because those axes hold the signal.
It retains the axes with massive shadows because they contain the signal, And it systematically discards the axes with tiny shadows because they contain only noise.
Let's take that a step further, because the concept of discarding axes becomes desperately necessary when we push this geometry to its limits. We have been comfortably visualizing our data in a 3D room, 3 axes.
It's cozy, it's intuitive.
But as we established earlier, a modern AI pipeline might operate in a feature space with 10,000 dimensions.
Or more.
When we scale the math up from 3 dimensions to 10,000 dimensions, does the geometry just act like a much larger warehouse, or does the fundamental nature of the space change?
The nature of the space undergoes a radical mind-bending transformation.
In what way?
The rules of intuition completely collapse. This brings us to one of the most notorious and fascinating roadblocks in all of data science: the curse of dimensionality.
The curse of dimensionality. That sounds ominous.
It is. The short answer is no. A 10,000 dimensional space does not act like a bigger room. In ultra-high dimensions, mathematical distance begins to behave in deeply counterintuitive, almost paradoxical ways.
Let's define the paradox. What specifically breaks down when we add thousands of axes?
The total volume of the geometric space expands exponentially with every new dimension added. Because of this massive runaway expansion of volume, the available space becomes unimaginably vast.
Okay, volume expands.
As a direct result, every single data point in your dataset gets pushed incredibly far apart from every other point. The very concept of closeness begins to evaporate.
Wait, hold on. I need to push back on that.
Okay.
If I have a massive data set, say 10 million customer records, surely if I drop 10 million dots into a 1,000 dimensional space, some of them are bound to end up clustered near each other, right? Density should still exist just by sheer numbers.
It is a logical assumption, but the math proves otherwise. Let's walk through a geometric thought experiment to visualize why density is destroyed.
Let's hear it.
Start with a simple 2D square on a piece of paper. It has an interior space and it has an outer perimeter.
Sure.
Now, extrude that square into a 3D cube. It still has a solid center mass and it has an outer shell.
Right.
Now, let the algorithm extrapolate that shape into a 1,000-dimensional hypercube. Mathematically, as the dimensions scale toward infinity, almost 100% of the total volume of that shape rushes outward, away from the origin.
Rushes outward.
The usable space concentrates entirely in the ultra-thin, spiky outer shell and the extreme corners of the hypercube. The interior center becomes a vast, empty void.
That is incredibly difficult to conceptualize. You are saying that in a 1,000-dimensional database, our 10 million customer vectors aren't forming dense clouds in the middle of the room.
No, they aren't.
They are entirely pushed out, clinging to the extreme edges and vast corners of this hyperdimensional structure.
They're completely marooned on the outer shell. And because every single point is pushed out to the extreme edges of this massive space, the physical distance between any two random points normalizes.
What does that mean, it normalizes?
They all become separated by roughly the exact same massive distance.
If every point is roughly the exact same distance away from every other point, then the foundational premise we built earlier, that closeness equals similarity, is completely annihilated.
That is the curse. Think back to the Python developer implementing the k-nearest neighbors algorithm we talked about.
KNN.
In a 3D space, KNN works beautifully because it can clearly identify a cluster of neighbors that are distinctively closer than the rest of the data.
But in 10,000 dimensions.
You pass a data frame with 10,000 raw features into a neighbors classifier. The algorithm will attempt to measure the Euclidean distances and find that the numerical difference between the absolutely closest neighbor and the absolutely farthest neighbor is trivially small.
Because they are all equidistant on the outer shell.
The distance is homogenized. The algorithm entirely loses its ability to distinguish between a highly similar customer and a completely dissimilar customer. The predictive power drops to random chance.
It's the equivalent of trying to locate your closest neighbor in a galaxy where every single star has expanded to be exactly 1 million light years away from you. The word neighborhood ceases to have any meaning.
The geometry defeats the algorithm. And this is exactly why machine learning engineers cannot just lazily throw every available column of data into a model and expect the neural network to figure it out.
So what's the solution?
The curse of dimensionality forces us to actively intervene. We must use dimensionality reduction algorithms to intelligently crush that 10,000 dimensional space down into a smaller, denser manifold.
Like squishing it down to 50 or 100 dimensions.
Exactly, shrinking it to a space where the concept of distance actually functions again.
Which perfectly sympathizes with the projection concept we just explored.
Yes.
We are forced to shine the mathematical flashlight, identify the 50 axes that capture the longest shadows, and aggressively prune the 9,950 axes that only contribute noise.
That's it.
By doing that, we shrink the volume of the space and force the data points back into a measurable proximity.
You are connecting the entire architectural workflow. We project the data to find the critical dimensions, we reduce the space to defeat the curse of dimensionality, and we measure the resulting distances to find similarity.
It's brilliant. We have meticulously built out this static geometric universe. We know how data is converted into vectors. We know how to measure the gap between their tips and the angles of their trajectories. We know how to scale the walls to prevent distortion. And we know the fatal dangers of letting the room gain too many dimensions.
A very solid foundation.
But a critical piece of the puzzle is missing. Up until this moment, everything we have discussed is frozen. A dataset sitting in a space is just an observation. But the term is machine learning. Learning implies an active process.
It implies an evolution of state.
Right. So how does a model actually learn anything inside this static geometric room?
Learning requires motion. And this brings us to vector operations. We establish that vectors are arrows, but it is vital to understand that they are entirely mutable.
They can change.
You can perform algebraic operations on them that physically alter their geometry. The two fundamental operations that drive all machine learning are vector addition and scalar multiplication.
What does the math of addition and multiplication look like as physical motion in our room?
Vector addition is the geometry of travel. If you take vector A and add vector B to it, you are plotting a path.
Like walking direction.
Exactly. You walk from the origin out to the tip of the first arrow. From that exact resting spot, you draw the second arrow and walk to its tip. The final destination is your new coordinate. You have physically moved through the space.
And what about scalar multiplication?
Scalar multiplication alters the properties of a single arrow. If you multiply a vector by a scalar number like 2, you stretch the arrow, doubling its length.
You just pull it longer.
If you multiply by 0.5, you shrink it. If you multiply by -1, you violently flip the arrow so it points in the exact opposite direction.
So addition governs changing your location in the room, and scalar multiplication governs how aggressively you stretch or reverse your trajectory.
Precisely. And these two rudimentary geometric movements are the sole mechanics behind the most famous, most powerful optimization algorithm in artificial intelligence gradient descent.
Oh, this is the peak of the mountain for a lot of developers.
It is the core algorithm.
When a junior dev opens a textbook on neural networks, the very first thing that intimidates them is the update rule equation for gradient descent. It is usually written out in heavy Greek notation, and it looks like insurmountable academic calculus.
It scares a lot of people away.
Let's dictate the equation for the listener right now and then dismantle it. It is written as theta becomes theta minus alpha times the gradient of j. Let me repeat that clearly. Theta equals theta minus alpha times the gradient of j.
To a programmer accustomed to reading Python loops, that equation looks completely opaque. But we are going to translate those symbols away from calculus and directly into the pure geometric motion we just defined.
Let's execute the translation. The first variable is theta. What does theta represent in our 3D room?
Theta is your parameter vector. It is simply an arrow pointing to the exact coordinate of your model's current guess.
Okay.
Imagine your untrained model is a small physical robot dropped randomly into our geometric room. The tip of the theta arrow is the exact square of floor where that robot is currently standing.
The robot is positioned at theta. Next, we have the gradient of j, represented by that upside-down triangle symbol. What does that symbol tell the robot?
The gradient of j is the vector of partial derivatives, but geometrically it represents the slope.
The slope of what?
Imagine the floor of a room is not flat, but contoured into a landscape of hills and deep valleys. The height of the terrain represents the error rate of the model's predictions.
So high up is high error, down low is low error.
Right. The gradient of j is an arrow that points in the direction of the steepest upward slope. It tells the robot, if you walk exactly in this direction, the error will increase faster than anywhere else.
So the gradient is an arrow pointing up the mountain of error. The final variable is alpha.
Alpha is a scalar number. It is your step size, commonly referred to as the learning rate. It dictates the magnitude of the movement.
Like how big of a step the robot takes.
A massive alpha means the robot is going to take a giant leaping bound. A microscopic alpha means the robot is going to inch forward with a tiny baby step.
Let's synthesize all three elements into the actual motion. The equation is theta becomes theta minus alpha times the gradient of j.
Let's walk through it.
The robot checks its current location in the room, which is theta. It calculates the direction of the steepest upward slope, which is the gradient. It multiplies that upward direction by its learning rate, alpha, to determine how far it should travel. But the absolute key to the equation is the minus sign.
The minus sign changes everything.
Because we are subtracting the gradient, we use scalar multiplication to flip the direction of the arrow completely backwards.
Exactly.
The robot looks up the steepest part of the hill, turns 180 degrees around, and takes a step of size alpha in the exact opposite direction. It physically walks straight downhill.
That is the entire secret of artificial intelligence. The robot recalculates its new position, updates the theta vector, checks the slope again, turns away from the upward gradient, and takes another step down.
It's just looping.
It loops this vector addition and scalar multiplication thousands of times, physically hiking down the geometric terrain until it reaches the absolute lowest point in the valley where it can no longer descend. That resting coordinate at the bottom of the valley is your fully optimized, trained model.
When a developer writes a PyTorch training loop and they set epochs equal to 100, they are literally just telling the robot to take 100 geometric steps down a mathematical hill.
That's all it is.
And when they tweak the learning rate hyperparameter, they are just telling the robot how far to stretch its legs on each step.
Exactly. And the geometry explains why tuning that learning rate is so volatile. If your alpha scalar is too massive, the robot takes a step so large that it vaults completely over the valley and lands higher up on the opposite mountain, causing the model to diverge and crash.
And if it's too small,
If the alpha is too small, the robot takes microscopic steps and the training process takes weeks to compute. It is a purely spatial navigation problem.
this reframing is incredibly powerful. The black box of machine learning is removed. It isn't a sentient brain-pondering data. It is an iterative geometric hiking trip executed through basic vector algebra.
It's just hiking down a hill.
Let's ensure this entire paradigm is permanently locked into the listener's workflow. I want to execute a translation drill to synthesize everything we have covered.
I love this idea. Let's do it.
In an industry environment, a junior developer is going to sit in architecture meetings and hear senior data scientists throwing around heavy academic jargon. It often causes imposter syndrome.
Oh, definitely.
I'm going to feed you 5 common, intimidating industry phrases, and I want you to instantly strip away the jargon and translate them into the simple spatial geometry of our room.
Let's build that translation reflex. Hit me.
Phrase number 1, you are debugging a model, and the senior engineer looks at the terminal output and says, we need to investigate this. The feature vector has an unusually large magnitude.
Spatial translation. That specific data point is physically located incredibly far away from the 000 corner of the room. It is geometrically isolated from the concept of nothing.
What does that mean practically?
In practical terms, it is a massive outlier, perhaps a fraudulent transaction or a corrupted data entry, and its sheer distance is going to severely warp the model's terrain.
Brilliant. Phrase number 2. The NOP team lead tells you, Euclidean distance is failing on these text embeddings. We need to compute the cosine similarity instead.
Spatial translation. Stop using the virtual ruler to measure the gap between the tips of the vectors. The absolute word count of the documents is distracting the model.
So what do we do?
Instead, look at the angles the arrows are forming. We need to measure if the arrows are pointing along the same trajectory to confirm if they share the same underlying behavioral or semantic pattern.
Phrase number 3. You are loading a massive, one-hot encoded pandas data frame, and the console throws a warning. Warning! The input data matrix is highly sparse.
Spatial translation. Almost all of the coordinate values for your vectors are sitting at exactly 0. If you visualize the 3D room, your arrows are not hovering dynamically in the center of the free space.
Where are they?
Because they lack values in most dimensions, the arrows are pasted flat against the walls or lying completely flush on the floor. The space is mostly empty volume.
Phrase number 4. A researcher reviewing your feature selection says, you can use both of these variables safely. The 2 features are mathematically orthogonal.
Spatial translation. If you draw the vector for feature A and the vector for feature B originating from the corner of the room, the angle between them is exactly 90 degrees. They form a perfect right angle.
What does a 90-degree angle mean for our shadows?
They cast absolutely 0 projection shadow onto one another. In business logic, this means knowing the state of feature A gives you absolutely 0 predictive insight into the state of feature B. They are entirely independent forces.
And finally, phrase number 5. This is perhaps the heaviest, most intimidating term in deep learning literature: the manifold hypothesis.
Spatial translation. Imagine you have a massive, terrifying 1,000-dimensional warehouse. The curse of dimensionality suggests your data should be scattered chaotically into the endless void. But the manifold hypothesis states that real-world data is not truly random.
It's structured.
The actual data points are densely organized along a much simpler, lower-dimensional surface, a manifold that happens to be contorted and crumpled up inside that larger warehouse.
Like a crumpled piece of paper.
Think of a flat, 2D piece of paper that has been crumpled into a tight ball and tossed into our 3D room. The neural network's entire job is to systematically unfold and iron out that crumpled piece of paper so it can draw a straight line through the data.
That translation drill alone completely neutralizes the academic intimidation factor. When you realize that the most advanced AI researchers in the world are fundamentally just describing physical shapes, angles, and shadows, the entire discipline becomes accessible.
It really does.
Let's bring this deep dive to its final synthesis. What is the ultimate mental model the listener needs to take away and apply to their Python code tomorrow morning?
The big takeaway.
The foundational truth is that spreadsheets and tables are a comforting illusion designed exclusively for human eyes. Algorithms are blind to tables. An AI model perceives your dataset as a sprawling, high-dimensional galaxy of floating coordinates.
A geometric universe.
It analyzes the system by measuring the physical distances between those points to determine similarity. It compares the angles of their trajectories to uncover behavioral patterns. It casts projection shadows to isolate the features that actually matter. And it iteratively moves its parameter arrows down the slopes of that geometric space in order to learn.
If you can internalize this single, unified spatial reality, you have successfully unlocked the black box of machine learning. The math is no longer abstract, it is visible.
The geometry provides total clarity. And the most exciting part of this framework is that today we have only explored the static half of the universe. We spent this session understanding how data exists in space.
We learned the anatomy of vectors and points.
But in the advanced tiers of AI engineering, spaces do not remain rigid.
That sets up our trajectory perfectly.
Yeah.
Where does the mental model go from here?
Well, in our next session, we are going to bridge the gap from the vectors we built today to the engine of transformations matrices.
Matrices. That is going to be fun.
We're going to explore how a matrix is not just a grid of numbers, but an active mathematical machine that literally grabs the fabric of our geometric room and aggressively rotates it, stretches it, and compresses it. Understanding how matrices warp space is the final key to unlocking the pure intuition behind principal component analysis, deep layer transformations, and advanced dimensionality reduction.
That is going to be a phenomenal exploration of the architecture.
For you listening right now, we have a mandatory call to action to cement this knowledge. The next time you open your IDE, when you load your next CSV into a Pandas data frame or run a SQL query, I want you to consciously pause, look at the columns, and force your brain to map them as axes in a room. Visualize where a specific row would physically float in that space. It will feel unnatural at first, but forcing that spatial translation is exactly what elevates you from a scriptwriter to an AI engineer.
Absolutely.
We also actively want to engage with your transition into the space. Drop into the comments below and write out any questions you have about Euclidean distance, vector projection, or navigating the curse of dimensionality. We read and analyze them all. And please ensure you hit the like button, share this deep dive with your engineering team, and subscribe to the channel. We are committed to building a community of highly practical, structurally sound, industry-ready developers here.
Before we sign off, I want to leave you with one final provocative concept to process on your own time. A thought experiment that pushes the boundaries of the geometry we just learned.
Leave them with something to think about.
We have firmly established that an artificial intelligence's entire universe is nothing more than a high-dimensional geometric construct. Every image, every line of code, every medical record is mapped as a discrete coordinate. So ask yourself this. As we deploy large language models to read the entirety of the internet, mapping every thought, conversation, and emotional expression humanity has ever digitized, what does the actual physical shape of human language look like inside that space?
Oh, wow.
What does the geometry of human behavior resemble when viewed from the outside? Are there massive, empty voids representing concepts we lack the words for? Are there incredibly dense, overlapping clusters around our core fears and desires? What does the structural geometry of humanity actually look like to a machine?
That is an incredibly profound framing of the technology. Thank you all for diving deep with us today, and we will see you in the next one.